In today's lecture, we are going to learn about Floyd-Warshall algorithm. So what's Floyd-Warshall algorithm? It's an algorithm to find all pair shortest path. So we are given a graph GV, E, so where there are vertices and edges. Okay, so we have to find the shortest distance between all pair of nodes. So how we will proceed? So we will use here a dynamic programming approach for solving this problem of all pairs shortest path. So let's see the problem statement. So given a directed graph, so we are given a directed graph in which all the edges have direction, and the graph may have negative edges. So it means some of the edges might be having negative weight. Okay, so if this is the graph, this is a negative edge weight, this is positive, and this is a positive edge weight. Okay, but it should not have a negative cycle. Why? Because if I have a negative cycle, so let's say this is -1, and here I can go again -2, and this is 3. So I can go from this A to C with the cost -infinity, because I can keep on moving in this cycle for infinite number of times. So my shortest path will be -infinity. So this should not be there in the graph, but it can have negative edges. So our question is, find the shortest path between all pair of nodes in the graph. Okay, so how to do that? So here again we will use dynamic programming, and we will try to formulate some kind of recursive solution. And let's see, so what will be that recursive approach of dynamic programming. So again, the sub problem, if we think about it, so it should be something like, if I have two nodes and let's say I have some node, so I can directly go between them, or if I choose some node, say let's say this one, then if this is the path P1, this is P2, then and this is a node K in between, then this P1 should be optimal and this P2 should also be optimal to obtain the optimal solution for the whole shortest path. Okay, so what we do is consider a subset of vertices from, and we number the vertices. So let there be n vertices, we number them from 1 to n, and consider a subset of V from 1 to k. So what we do, we consider a subset of V from 1 to k, and for any vertices I and j in the graph, we consider all paths from I to j. And what happens, we consider, take two nodes I and j, and we consider all paths from I to j with the constraint that whose intermediate vertices are drawn from vertices 1 to k. So what it means really is that, let's say I have just 4 nodes. This is 1, 2, 3 and 4, and I am asked to find the shortest path from 1 to 4. Okay, and if I write like, let's say I have to only use something like, the path should only be from node 1 to k. So here k is 2. So this means that distance from node 1 to 4 using only intermediate nodes as node 1 and 2 Okay, so it means I can choose in this graph, I can either choose 1, 2, 4. So this is one possibility, 1, 2 and 4 I can traverse here, and let's say all edges are of weight 1. So this is one possible path here. Another possible path is 1 and 4 directly, because I am not using any intermediate path. So 1, 4 is also fine. So another thing we can do is, let's say D3, 1, 4. So here it means I can choose intermediate nodes as 1, 2, 3, all of them. So I can have something like 1, 2, 3, 4. So this is one path, and then 1, 2, 4 is another path, and 1, 4 is another path. So this is the meaning of Dijk. So where K means I am choosing the intermediate nodes in the path from 1, 2, 3 till K, and I and J are the source and the destination nodes. Okay. So now let P be the minimum length path from among them. So let P be the path which has the minimum weight. So we will now try to form some recursive solution, and that's what we represent, Dijk. So this represents, it is the minimum distance path from node I to node J, with the intermediate nodes in the path being from node 1, node 2, node 3 till node K. So this is the definition of Dijk, the shortest path from node I to node J with intermediate nodes from V1 to K. Okay. And we saw the example here. To illustrate once again, we might see one more example. So let's say this is 1, 2, 3, 4 and 5, and all of them are mostly, so it's kind of a click graph where all the nodes are connected to each other. So now if I say that, okay, D2, 5 and let's say 3. So what it means, there can be how many different paths? Let's try to enumerate, because this is the thing we are going to use in our dynamic programming. So D3, 2, 5 means, so I will be taking this node and this node, and let's try to see what are the paths possible. So I will only be choosing from nodes 1, 2 and 3. So I can use those 1, 2 and 3. So I can go from where D1, 2, 1, 5 I can write 2, 1 and 5. So I'm just using first intermediary node, and then like we can have 2, so I can use 3 also. And let's say we had one edge here also, because this is a click graph. So 2, 3 and 5 is another one that we can have, and 2, 1, 5 we can have. Similarly, if it is 1, 5 using 4, so 1 to 4 nodes, so we have 1 to 5. I can directly have 1 to 5 is possible. So I will write all the possible solutions. 1, then because I can use till 4 nodes, so 1 to 2 I can go 2 to 3, and I can use the 3 to 4 and then 5. So this is also possible because intermediate nodes are 2, 3 and 4, which is possible here. And we can also have 1 to 2, 2 to 3 and 3 to 5 directly. So here also I'm just using nodes 1 to K, where K is 4. So this is fine. So this is one example to make you understand the meaning of Dijk. Okay. So now we will try to formulate the dynamic programming equation. So now Dijk will be equal to Wij if K is equal to 0. So what it means, if I'm choosing no node, if I'm allowed to choose no node in the intermediate path, then Dij0 will be what? It will be always equal to Wij, and if there is an edge in between with some finite value, then that will be the weight of the minimum length path. And if it is if otherwise, if it is connected through some intermediate nodes, so it will be 0. Okay, and that the adjacency matrix representation takes care of. But otherwise, what happens if I am to choose from k minus 1 nodes? So this represents what? Dij k minus 1. So it means I have a shortest path from node I to j using only the first k minus 1 nodes, and it means I am not basically, so it's a decision problem. So I am here not choosing, so I'm not choosing, so node I is not in the, so node k is not in the shortest path from node I to j with k nodes as the 1 to k nodes as intermediate steps. Okay, but if there is kth node in between, then what will happen? So this will be the kth node. So first path will be here I, and then j will be there. So this k will be the intermediate node. And now what I can say, because I have already know all the paths from I to k using k minus 1 nodes. So this is P1, this is P2. So P1 is di to k using k minus 1 nodes, and this P2 is dk to j using k minus 1 to k minus 1 nodes. And these two in the shortest path using kth node, they will form the shortest path using optimal subproblems property. Okay, so this is what is represented here. So I have the kth node now, kth node is there in the shortest path, kth node is present. Okay, so in that case what happens? It will be the shortest path from node I to node k using first k minus 1 nodes, and then node k to j using first k minus 1 nodes, and whichever is the minimum, so I will choose that. So this is the important equation that you have to understand. And finally, to solve the problem, so in the end all the nodes we can use the intermediate nodes from node 1 to n, and this matrix dn dij n gives us the final shortest path using all possible nodes 1 to n. So let's take one example to make the things more clear. So I have a graph. So 1 2 3 4 5 nodes are there and weights are assigned. So weight from a node I to I itself is 0 because it is there itself, and if a node, two nodes are not connected, so its weight is infinity. So this is the representation of the adjacency matrix, and we can see that okay, node 5 to 2, so 2 to 5, it will be represented as 2 to 5, we see, so its value is 7. If say node 2 and 4 are connected, so let's say which are not connected, 3 and 5 is not connected, so it is infinity here. Okay, so this is the adjacency matrix representation. So this is the adjacency matrix, and now what we try to do is, so this is also the D0, which means what? I cannot use any intermediate paths. So if two nodes are directly connected, so that will be the D0 ij, and if they are not connected, so it will be infinity. So let's see, D0 2 comma 4, so 2 comma 4, so they are they connected? Yes, 2 4 is connected, its value is 1. So D0 2 4 is 1. Similarly D0 3 comma 2, so 3 to 2 it's connected and weight is 4. Similarly D0 3 comma 5, 3 to 5 is not connected, so I am not choosing any intermediate node, so that's why its weight is infinity. D0 4 comma 4, as I am already at that node, it will be 0. Okay, so I think this is clear. D0 and the adjacency matrix are the same. D0 is equal to adjacency matrix of the graph. Okay, so now let's proceed further. So I have taken example, and so D1 can be calculated. So I have calculated D1, so this is D2. So D1 means what? Now all the distances from node I to j are using just the first node from 1 to 1, and this is from 1 to 2 nodes I have used. This is D3 means in node ij I can take 1, 2, 3 as the intermediate nodes. D4 means I can take 1, 2, 3, 4 as the intermediate nodes, and the graph has 5 nodes. Now D5 is the final matrix, so it has all the nodes from 1, 2, 3, 4, 5 in the intermediate path. So let's see some calculations. So let's see how D142 is calculated. Okay, so D1, 4, 2 means what? It means, so from the graph, let's see, D1, 4, 2, it means I have to go from 1 to 4, and I can choose only nodes 1 and 2 as the intermediate node. So D1, 4, I can use this one, so I can go from here D1 to 2 and then 2 to 4. So this way I can go, because node 1 and 2 are allowed in the intermediate path, so this is fine. And even D1 to 4, 2 can be directly, can we go from 1 to 4? In fact we cannot, so it is infinity. So let's see. So these are the two possible paths, and I will take which one? Whichever is the smallest. So here it was D1 to 4 directly was infinity, 1, 4, because it is not connected. It is only a directed edge from 4 to 1. So we move further. So we see D1, 4, 2 is minimum of, if I'm not using the second node. So what will happen is that then it will be D1, 1, 4, or otherwise if I'm using the second node, which is the kth node, it will be a path from D1 to 2 using just 1 to 1 node, and D2, 4 using just one first node. So this one, if we see, so D1, 1, 4 is this one, so 1, 4 is infinity. D1, 2 in this one is 1, 2 is 3, and D2, 4 is 1. So we see that this comes out to be 4, and this is infinity. So minimum of them is 4, which we see that, okay, when we go from 1 to 4 using just node 1 and 2, so minimum will be 3 plus 1, which is 4. So that looks fine. So similarly, let's try to calculate one more. So D3, 5 using node 1 and 2. So let's try to see from the figure. 3 to 5 using just node 2 and 1. So what will happen if we see from the graph? So it's from 3 to 5. So from 3 to 5 I can go via 2, and then from 2 to 5. So this is 4 plus 7, 11. And can I go via 1? I cannot go. That path is infinity. Okay. So again, try to see from this code. So it will be minimum of D1, 3, 5. D1, 3, 5 means what? I have to go from 3 to 5, and I can just use node 1. So 3 to 5 using just node 1. So it is infinity. And if we see from the graph also, so D1, 3, 5 is infinity, which is visible from the graph, and otherwise if we choose the second node, so I have to go from 3 to 2 using node 1 just, and then 2 to 5. So we see here, so 3 to 2 is 4, and from 2 to 5 it is 7, so it is 11, and that's what we saw. So between 3 to 5 using just node 1 and 2, so I could go from 2 and 2 to 5. So it was 4 plus 7, 11. Okay. So this is the calculation. Similarly, I have calculated D3, D4, D5. So let's try to do one calculation D5 1, 3. So what it means, D5 1, 3 means final calculation, distance between node 1 and 3 using all nodes as intermediate nodes like 1, 2, 3, 4, 5. So D1 to 3. So I have to go from, let's see, it is D1 to 3. I have to go from node 1 to node 3. So node 1 to node 3, I can use all the intermediate nodes 1, 2, 3, 4 and 5. So I can go from 1 to 3 directly. I can take some intermediate nodes, like I can go from 1 to 2, then 2 to 5, then 5 to 4 and then 4 to -5. So how much is that? 1 to 2, 2 to 5, 5 to 4 and 4 to 3. So this 1 to 2 is 3 plus 2 to 5 is 7, 5 to 4 is, now what, it is 6, and 4 to 3 is -5. So it is 10 plus 6 16, -5 11. So let's see. So if we see, so okay, so that is one of the path, but there are other paths which are giving us lesser value. So one is D4 1 to 5 and D5. So I'm using the fourth node, and D1 to 5 using first 4 intermediate nodes, and D5 to 3 using 4. So it is coming out to be -3. So the shortest path has value -3 from 1 to 3. So it can be like, see here, 1 to 5, so it will be -4 plus 6 plus 2 -5, it is -3. So I am using a path 1 to 5, 5 to 4 and 4 to 3. So this is costing me just -3. So this was about the Floyd Warshall's algorithm, and it uses this kind of that, okay, Dij means I am using distance from node I to j and using 1 to k nodes, and this iteratively if we perform till Dijn, it gives us the shortest path from all nodes.